In this video, I will be taking you through the process of creating a Minecraft clone rendered in the terminal from scratch. So the first thing we're going to add is the world size. This allows us to control how big we want the world to be and will be used in the blocks array. The blocks array is a 3D array of chars and will represent the entire world. An empty char will represent air and any filled in char will represent a solid block. Eventually, different chars will correspond to different colors. The next thing we're going to do is create a 2D array called the picture. This is going to store the final image we're going to display to the screen. Now we're going to create two variables to store how many x pixels we have and how many y pixels we have. Ideally, we want some sort of way to control how many x pixels we have and how many y pixels we have. That way, the player can decide on the resolution they want to see. To do this, we'll need to import the scanner class in order to take input from the player. This is going to be one of the two inputs we're using throughout this entire code file. Now we're going to create the scanner object, and then we're going to create a variable that'll store our extra resolution. This is going to be used to scale up our x pixels and y pixels, effectively changing our resolution. Next, we're going to actually allow the user to modify this value. Now this while loop is going to take in the extra scale value from the user and just verify that it's valid before breaking and updating the x pixels and y pixels here. Next, we're going to implement a boolean array of key states. This is going to be used to process input. Now we could have just done a switch statements for all the possible keys, but this system is more dynamic and will eventually allow us to have non-blocking input, as we'll see later on. Next, we're going to have a method to initialize the blocks array. Right now it's not going to do anything, but eventually we'll define it. The implementation of this blocks method is going to be fairly straightforward. We're just going to loop over every element in the blocks array and then first set them to be the air block, which is just the empty char. And then we're also going to loop over every block again, but this time we're going to set some of the blocks to be filled. So every block below z level 5 is going to be the at char, which basically just means it's going to be solid. Before we move on, we're going to need a vector class to be able to handle all our calculations. First, we define a constructor to initialize the vector. We also have a method to add two vectors, subtract them. We're also going to have a method to scale a vector by some double. And then finally, we're going to have a method to normalize the vector. First, we're going to calculate the length, which is given by Pythagorean theorem. And then, if the vector's length is valid, we're going to divide all the components of the vector by its length. We're also going to need a much simpler vec2 class. The only thing we've defined here is the dot product method, which we don't actually need for the vector3 class. We're going to have one final class called the player class. The player class is going to represent where the player is and where the player is looking. We're going to have a vector3 to store where the player is, and then we're going to have two doubles called phi and psi, which are going to store the rotation of the player. Phi and psi come from spherical coordinates, which is what we are using to describe rotations. Spherical coordinates use a radial distance and two angles to describe a vector, while Cartesian coordinates just use three distances. Now, since these vectors are normalized, the radial distance is always 1, so we can actually just drop it out. Next, we set the position on the x and y to 50 because we want the player to spawn on the middle of the world. Ideally, we should be dividing y blocks and x blocks by 2 and then using that as the player's x and y position, but I'm lazy, so we're going to stick with this. Next, we're going to create two variables to control the height and width of the viewing plane. The purpose of the viewing plane will be explored shortly, but for now you can just assume it has something to do with rendering. Now we're finally going to get to the meat of our code. Here we're going to call a function called getPicture, which is going to effectively render our game. It's going to take in the view plane, the x pixels and y pixels, the world dimensions, the player, the picture, and the blocks array. We also need to define a block border, which is just going to control how thick the outlines are for the block. we could actually just do it right here. Go. We're also going to have a draw ASCII function. The draw ASCII function is going to take in the picture array and then output the final image to screen. Eventually, we're going to be passing in the colors array, and then the draw ASCII function is going to be handling colors. But for now, we're going to leave it as is. Now we're going to move on to the actual implementation of the getPicture and draw ASCII functions. The getPicture class is actually pretty complicated. So before I go into the explanation, I have to explain some of the preliminaries. You might be asking how exactly we are going to take a 3D world and create a 2D image that we display. And the answer is ray tracing. For every pixel on the screen, we are going to create a view direction. This view direction is going to be used to shoot rays from the screen to the world. Once a ray hits something in the world, it reports back to us and tells us the color of what it hit. This is a simplification, but it is sufficient for an analogy. Besides, I am going to show you the code, so at the end of this, you will know exactly how this all works. So the init directions is going to initialize the viewing plane, and the ray trace function is going to fill the picture array with characters depending on whether or not a block was hit, and what type of block was hit. Before I go on to the init directions method, I have to explain the angles to vect method. The angles to vect method is going to be a helper that's going to be used inside the init directions method. All it does is take in two rotations, again these are for spherical coordinates, and it's going to return a vector 3 representing that rotation. Basically, this function goes from spherical coordinates to normal Cartesian coordinates. Now in the init directions class, first we grab the player's rotations, and then we initialize some vectors corresponding to directions on the viewing plane. Using those directions, we're going to create 4 more directions, which are the actual directions we're going to be using. Next, we're going to create a 2D array that's going to store a direction for every pixel on our screen. Basically, inside this block of code, we just mix these 4 vectors depending on the x pixel and y pixel we're working with. Once we're done with that, we can return the viewing directions array. Just to help solidify this method, the dir array corresponds to the directions all those rays are facing. Going back to the getPicture class, we can see that after we get the viewing directions, we loop over every pixel in our final image, and then we call a ray trace function where we pass in the directions we just calculated. Now, in the actual ray trace function, first we initialize the origin of the ray, which was passed in as a parameter. And while the ray isn't outside the world, and I'll show you how this method works exactly in a second, we grab the block that the ray is currently inside of, which initially is just the origin of the ray. And then, if that block isn't an air block, which is the empty char, we call another function called onBlockBorder, which will basically tell us if we're looking at the border of the block or like the middle of the block. If we're looking at the border, we return the minus sign, and then if we're not looking at the border, we're just going to return the character associated with the block. The reason we're doing this minus sign thing is so that we can tell where the edges of the block are. Moving forward, this block of code tells us how far we can move the ray in its direction before it hits the next block. And this block of code is actually responsible for pushing the ray. Once we're done pushing the ray, we go back to the start of the loop and check if the new block we're inside of is an air block or not. We basically keep looping through this until we hit a block or we exit the world. The onBlockBorder method is fairly simple. First, we take in some position value and then get its fractional components. The reason we do this is because the fractional components will tell us where inside a block a point is, because each cube has a width of exactly 1. Now, if the point is close to any of the edges, then we increase the count value. If the count value is greater than or equal to 2, then we know the point is on an edge. The RayOutside method basically just tells us if a point is outside the world or not. A point is outside the world if any of its components are negative, or if any of the components are outside of the world bounds, given by the x blocks, y blocks, and z blocks. Now, going back to the main method, since we've implemented the getPicture method, all we have to do now is implement the drawASCII function. The implementation for the drawASCII function is pretty simple. First, we reset formatting and move the cursor to the top left. Next, we create a string builder class. The string builder class basically just lets us work with strings in a much more efficient way. Then we loop over every row of pixels, output a reset code, which basically resets colors, and then we write the character stored in the picture array to the final string we're gonna output to the screen. Note that if a character is null, then we're gonna switch that null into an empty space. And then after that, we're gonna reset the colors and formatting once more and skip to the next line. Resetting the colors right now doesn't really do too much, but later on, once we do add in colors, we're gonna need these lines. For now, we'll just leave them as is, even though they're not being used. After that, we're gonna append this sequence of text to the bottom of the image. This sequence of text basically just tells us the controls. Right now we don't have any controls, but once we do have controls, we're gonna need them. We're also printing the player's position and the player's rotation. For rotation and position, we're using a round to helper I created, which basically just rounds a decimal number to 2 digits. After compiling our program and running it, we will be prompted for a resolution. For now, we're gonna type in 4, which is the default, and we're gonna get this. It looks like this because our terminal window is too small. Since I'm using VS Code, I can just hit Ctrl- to make the terminal window resize. Once I do, and I scroll back up, maybe zoom out once more, scroll back up, we'll see something that resembles Minecraft. As you can see, the grid lines tell us where each block starts and stops. Now, a core part of Minecraft and really any FPS game is that we're allowed to move the player. So the first thing we're gonna have to do is create a game loop. For this, I've created a while loop, and inside the while loop, we're gonna be calling a process input function. Now, the process input function is gonna take in a scanner and a boolean array of key states, both of which we created before. Next, for every single key state, we're gonna set it to false, and then we're gonna ask the user for input. Once we've received input, we're gonna set the appropriate key in the key state array to true. Note that this means that the game isn't gonna be rendering until we press a button. Unfortunately, there isn't any easy way to get around this without importing more libraries. If I do make a part 2 of this series, I'll show you guys how to make non-blocking input so that as soon as we press a key, it'll move the camera and that the game is going to be running even if we're not pressing anything. For the update pause view function, first we're going to fetch the position of the player and its rotation. And we're also going to initialize what's effectively the moving speed and the rotating speed. Next, we're going to clamp the player's position to always be within world bounds, or at least the X and Y components of it. We're also going to grab the block we're standing on. If it's not a solid block, which means we're inside of a wall, we're just going to push the player up. This is a very basic way to handle collisions, but it will do for now. Next, what we're going to do is check if we're in the air. Effectively, what we're doing here is applying gravity. Now, we're not actually accelerating, but again, this is a basic implementation. Next up, we're going to check for rotation input. If we're pressing any of the keys, we're going to rotate by the tilde epsilon value. Then we grab what's effectively the forward direction. We use this so that once we press any of the moving keys, we can actually move in the appropriate direction. That way, pressing W is going to move us forwards or in the direction we're looking instead of some random direction in the world. After we've processed the input, we reassign the player's position and the rotation values. We're also going to implement a simple clamp function which takes in a number and a minimum and maximum bound and returns the number if the number is within the bounds or the min or max depending on whether the number exceeds the bounds or precedes it. Now after we've processed input, we can repeat the draw picture and draw ASCII commands. Now, inside of our game loop, we're going to be processing input, updating the position and view of the player depending on that input, and then re-rendering the game. If we compile our game again, we're going to get the exact same image, but this time, if we try rotating the camera by pressing L and then the enter key, we'll see that we're rotating. If we press K, we'll see that we can look down, and if we press I, we can see that we look up. And we can also move using WASD. The next thing we're going to want to do is add the ability to break and place blocks, because that's a core feature of Minecraft. To implement breaking and placing blocks, the first thing we're going to have to do is to have some way of getting the current block that we're looking at. After that, we're going to check if the current block is even valid. Next, we're going to grab the actual integer coordinates of the block that we were looking at, so that we can access that block in the blocks array. After that, we're going to create a saved char variable, whose purpose is going to be made clear in a second. We're also going to have a boolean removed, which is going to check if we've removed the block or not. Then, if the current block is valid, we're going to set the saved char to the current block. After that, we're going to index into the blocks array and then set that char to lowercase o. This is to help us visualize the block that we're staring at. Now, if we're pressing the X key, we're going to set removed to true, and then we're going to set that block to air. That handles breaking blocks. The next step, logically, would be to implement placing blocks. So, if we press the space key, we're going to call some function that's going to place that block. Now, current block is eventually going to be the type of block we're placing down, but for now we're just going to set it to be the add char. Now this chunk of code is going to set the block that we're looking at to have the O key, but if we look away from that block, then that block's char should reset back. This bit of code does exactly that. So if we have a block and it wasn't removed, then we're going to set that block back to the saved char. The implementation of the placeBlock function is actually fairly simple. First, we're going to grab the integer coordinates of the position we're trying to place the block. Then we're going to grab the fractional parts of each block as such. Now this bit of code is going to tell us the distance from our pause to each face of the block that we're looking at. This is a very basic way of checking what face a point lies on, but for now it's good enough. After that, we're going to fetch the lowest of these distances, and then, if that block is valid, we're going to fill it with the block that we want to place down. Now, the getCurrentBlock method is fairly similar to the raytrace method, but instead of using a view direction, we use the player's rotation. Then, we do the same while loop that we used in the raytracing function to find the block that we're looking at. Once we found a block, we return the position of that block. Now, compiling our project and rotating the camera, you can see that the block that we're looking at is discolored. This is because we've set that block to be the lowercase o character. And the lowercase o character is kind of hollow, so we see more of the back of the terminal, which is black, which is why the block is discolored. Now, if I press the space key, we should see, very roughly, that a new block has been created. And if I press the X key, looking at that block, you should see that it gets removed. Next, we're going to implement the Berlin noise algorithm for the rendering of terrain. First, we're going to create an integer array of length 512. We're going to fill that array from numbers 0 through 255, and we're going to shuffle the array. Once we're done, we're going to copy half the array into the other empty half. Now we move on to the actual noise algorithm. We're going to take an x and y, which represents the point we're sampling, and the permutations array. We're going to make sure that the point x and point y are modulo 256 and that they're not negative. Next, we're going to get the distances from the point to each of its grid cell corners. After that, we're going to get the constant vector for each corner. Then we're going to take the dot product between the distance to the corner and the constant vector at that corner. To make the result smooth, we're going to grab the x component and call the fade function on it, which maps that component to a curve. We're going to do this for the y component as well, and then we're going to linearly interpolate all four of the components we just created up here by basically how close we are to all of them. Now the lerp method is fairly simple. If the input t is 0, we're going to return a1. If the input t is 1, we're going to return a2. The fade function is something I found online, and its specifics don't really matter too much. But basically, again, it just helps our noise algorithm be more smooth. With all of that said and done, we're gonna come up here and initialize the permutations array. Next, inside of the initBlocks method, instead of just creating a giant rectangular array, what we're gonna do first is sample from the noise texture. I'm gonna use the scale value here, which basically just controls how big the noise texture is. For our purposes, the scale value is just gonna control how fast hills and valleys change. We're also gonna pass in the permutations array. Next, we're gonna normalize the output from sampling the texture so that it ranges from 0 to 1. Using this normalized value, we're going to map it to a range of 1 through 6. We're going to use this new value called iter to decide how many blocks up high we're going to build till. For example, if iter was 2, we would set every single block beneath the height of 2 to solid, represented by the @ character, and every other block above 2 would be air, or the empty character. And then finally, all we have to do is declare the scale value and the permutations array. Again, permutations array is going to be passed in as a result from the make permutation function. Compiling a program, running it, and then opening the window, you can see very roughly that we have terrain. Right, like look at the block I'm looking at. Clearly you can see it's in some sort of valley, or some sort of hole, I guess. And the block over there is on some sort of hill. Now, it would be really nice if we could see the terrain much more clearly. To do that, we're going to have to add in colors. In order to handle color, the first thing we're going to have to do is create a byte array called color. For every pixel, this byte array is going to correspond to a color for that specific pixel. The next thing we're going to do is pass in colors as a parameter to get picture, draw ASCII, and then inside get picture, we're going to pass that into ray trace. Inside the ray trace method, we're going to call a method that takes in a character and returns a color for that block. The get color for block method is fairly simple. Basically, depending on the character you pass in, it returns a different color. So in this case, every block in our world, which is currently represented by an @ character, is gonna correspond to the number 24, and every lowercase o, which in our case is every highlighted block, is gonna correspond to the number 0. These numbers are then converted into string color codes. 24 corresponds to green, and 0 corresponds to black. The rest of these numbers are unused for now, but will be used later on. And the next thing we're gonna do is modify the draw ASCII method to account for color. Basically, we are gonna have a byte current color which tracks the color we are currently printing to the final image. The only reason we use this is so that we don't append repetitive color codes for every single character. This is kind of an optimization. The reason that we can get away with this is because if you add a color code to the start of a string sequence, Java will continue printing that color up until a reset flag or a different color. After we compile and run, we should see color. As you can see, every block is green, except for the block that we're looking at, which is black, exactly as we wanted. An unintended consequence of our system is that because we output minus signs for the border of each block, the border is going to be a slightly different color from the actual block. This is because the back of the terminal kind of blends in with the color, which gives us this nice effect that we don't even have to work for. Okay. The fix is simply to clear the colors array before we render each frame. That way, stale data from the previous frame doesn't carry over. And as you can see, the ghosting effect is gone and we're getting colors properly. Finally. Now, the next thing we're going to want to do is add textures. To get textures working, the first thing we're going to do is inside the ray trace function, we're going to call some sort of method called getUVs. Basically, it's going to take in a hit point, xyz, and tell us the UV coordinates that we hit in the x and y component, and in the zi component, it's going to tell us the face that we hit. So 0 if we hit the first face of the block, 1 if we hit the second face, and so on. The getUV method is fairly simple. We do the same kind of checking that we did for placing the block, and based on the face we hit, we set the U and V components accordingly. Now the actual math behind getting the UV coordinates is probably wrong for my implementation, but when I tested it, the textures seemed fine, so that's what we're gonna go with. We're also gonna store the face ID because it's useful for when we're grabbing textures. We're gonna pack all of that data into one vector 3 and pass it back. Next, we're gonna go to the getColorForBlock method and modify it as so. The grass top, dirt texture, and grass side are all 16 by 16 textures that store an integer that corresponds to a color in each element of their arrays. For example, you can see that the dirt texture looks something like this. Now remember, these numbers map to colors in the ANSI color function. Notice that depending on the face, we use different textures. So if it's the top face, then we use the grass top. If it's the bottom face, then we use the dirt texture, otherwise we use the grass side. We multiply U and V by 16 because U and V both range from 0 to 1. We convert them back into integers so that we can actually index into the array. Next, we're going to modify the call type for the getColorForBlock function to pass in the data we calculated in the previous getUVs function. That is after we convert data.z into an integer. Running the code, you can see that we've got something that resembles textures. Doesn't really look too well, but that's just the limitations of using a terminal. The next thing we're going to do is implement trees. We're going to go into the initBlock method, and then for some of the surface blocks, we're going to create a tree. Now the createTree method itself is fairly simple. First we create the bark of the tree, and then we create the leaves of the tree. It's nothing really complicated, it's just more of a stylistic thing. Note that we use a percentage symbol for leaves and the hashtag symbol for wood. Next, we're going to come back down to the getColorForBlock method and add in the two cases for the leaf and wood block. We're also going to add in the leaf and wood texture up here. Note that these textures were created from images that were pre-processed by a Python script. Now, if we run the script, we can see that we have trees. To be able to place down different types of blocks, first we're going to have to add in a variable to keep track of the block we want to place. Then, depending on the key pressed, we're going to change the current block to that appropriate block. And instead of placing down the add char, we're going to place down the current block. We're also going to want to modify our getColorForBlock method to be able to handle the different colored blocks. Really quickly, before we check if we can place down different colored blocks, another thing we can add in is water. All we have to do is add in this one line, and now if the surface dips below z level 2, we're gonna have water. Running our program and pressing space key, you'll see that we've now placed down a green block. If we hit 2 and then place down another block, we'll see that we placed down the red block. Now let's try and look for some naturally spawned water. And as you can see, when the surface dips below z level 2, instead of placing down air or a solid block, we'll place down water.